Okay, so welcome back to the second lecture of geometry on minimal surfaces. In this series, I will be explaining what I understood from a seminar I attended. And in the first lecture, I tried to motivate why we study the bending energy of a given curve, right? And so when it comes to minimal surfaces, rather than worrying about the energy of a curve, we worry about the energy of a plane. So let's try to make the gap. Okay, wait, let me connect my pad. Yeah, okay. So we try to make the connection between the curvature of a line, and we want to generalize it so that we can say things about planes. Right? So this is mainly what is studied. How do we, if we can assign an energy to this line over here, which was given as E, right, in the previous thing, how can we assign an energy to a plane? Okay. So Ulrich's talk begins with stating that given a line, you can define its bending energy. Before it was written as B in his textbook, or it is also written as E, which is given as the integral from 0 to L, which is the length of the curve, so we're integrating over a curve gamma, right? And I haven't mentioned that here, gamma. For surfaces, we use the notation of sigma, okay? So sigma is equal to a surface, okay? And gamma is equal to a curve. So we take the mod of the double derivative of our curve and square it. So this is why, what do you say? When I'll explain how this part comes really quickly. So if you remember, B is defined as integral 1 by 2 from A to B, the inner product of dt by ds, comma dt by ds. Okay, over ds, I think, I'm not sure. And what do you say? It's pretty easy to see why these two are equal, and it comes from the simplified key. And this is t at any point. T is equal to the first derivative of this. The tangent is given by the speed of the curve, or just the first derivative of the curve. I say speed because we kind of use that terminology quite often just to understand things. So speed slash derivative, right? And now we're taking dt over here. So dt by ds is the same as gamma double dash. Okay, so this part is clear. And we're taking the inner product with itself. So that's sort of like dt by ds, the whole magnitude square. Okay. So this is equal, these two are equal to each other. And we know this. So checking this part and this part into here, that's how we get this. Okay. And A to B is just changed over here. So we say ki, if this is the interval A to B, the only thing he's changed in this presentation is that instead of taking it as B minus A as the length, we just say that the length is equal to L. So integral goes from 0 length to L length. Okay. And that's bending energy. So I am pleased that we understand it well enough now, because that's good. Because that makes things a lot clearer for me. Yeah. Okay. So okay. So now we put some conditions. Okay. So when we talk about bending, right? Suppose this is a tight wire. We can't really make this, we can't really deform this without, what do you say, if this is a rigid wire, right? So you can't deform it any further. Now if we take away rigidity and we put in elasticity, hooray, your thing can stretch, wait, let me just, yeah, if your line looks like this, it can stretch, right? Just a physical picture, what do you say, visualization of what we're doing, right? We can stretch it and do all sorts of, and technically this is what counts as a deformation. Now deformation, formally defined, is like if you have a line like this and if you have some other line like this, right? This is gamma 1, this is gamma 2. If gamma 1 is homotopic to gamma 2, then the map D, let's not take D, let's just take, I don't know, F, that takes gamma 1 to gamma 2, is a deformation. Okay, so what this means is that gamma 1 and gamma 2 are topologically equivalent. Okay, so yeah, this is a line and this is still a line. So lines are, any given line is homotopic to another given line. Now let me give you an example of what is not homotopic. This line is not homotopic to, say, a circle. Okay, I cannot smoothly bend or deform this so that I can get a circle. However, I can smoothly deform this to get a squiggly line. Okay, so that's the idea of what a deformation is. Now we know what kind of deformations we have. The question is there a particular type of deformation I have to worry about? So when we're talking about elasticity, elastic deformations. So when we're talking about elasticity, our deformations are going to follow the following properties. Okay, so deformations, at least when it comes to lines, okay, we're talking strictly about lines here. So the deformations need to be the following. They need to be length preserving. And what do you say? They need, or in other words, they need to be isometric. And they need to allow only compact support. Now what is compact support? So compact support in this case, when I say something is compact, right, it means it is sort of like it has a boundary. So for example, in topology, the notion of compact would say, okay, if I have a space that looks like, say, a donut, I would say this is compact because there is, like, the rest of the space out here in which this thing is not a part of. Yeah, everything that lies in here lies inside this thing, and an example of something that is not compact, it's better to explain with counter examples. So not compact, oh wow, okay, yeah. Compact example would be, say, I have a space that only considers the top of the R2. So given R2, if I only consider the top space, then that is not compact because it's not really bounded. It's only bounded by this one line at the bottom. It's not bounded anywhere else, right? So this is not compact, whereas this is compact because it's bounded by the boundary of the torus. Now similarly, another example of compact is if I have just a plane like this. So this is like a sheet, and it has some sort of like hill over here. It has this boundary like this. So this thing is also compact because beyond here it is bounded by this thing, right? However, there is one distinction between this compact surface and this compact surface, and that is the idea of closed. So a closed surface in this sense, now I'm going to change what I mean by boundary, okay? So when I mean by compact, it means it is like, it's not infinite, rather. A better wording to say when something is compact is that its volume or the space it spans is not infinite. So what this change, my change of phrase, right? It holds good to still distinguish between our surface. Let me just use a highlighter. Is a highlighter on? No, it's not. Yeah, it's still good for distinguishing between this upper plane surface and these two things, right? It's still going to distinguish between our torus over here and our compact surface over here. But the difference lies in the fact that this compact surface here has a boundary, has an explicit boundary, which is this line, this curve that surrounds it, the shape surrounds the surface. Whereas you cannot say the same thing. So both of these have finite area or finite volume, but this is bounded by an actual boundary, whereas if you try to draw the boundary of a curve, you can't really draw one single line that completely covers your curve, right? Or one single plane that covers your curve. So that's a layman way of understanding what it means for it. And so all this to say that in some sense, compact means it's both not infinite and it has a boundary, right? So if I draw a function that looks like this, you see how here in this interval and this interval, beyond which it is 0, right? Here also it's 0, throw it this way and throw it this way. And only here it is greater than 0. And this boundary, A and B, is well defined. So the boundary of this curve, if this curve is gamma, then the boundary is denoted by delta of gamma. Okay, so watch out for confusing notation. So similarly, let's just dwell on the notation of boundaries for a bit. This line that I showed over here, if this surface is sigma, then this line over here is delta of sigma. Okay, so this delta means the boundary of gamma. Okay, now the boundary is well defined, that is, the boundary is basically A and B, right? But are the points A and B, but everywhere within here this is both finite and it is bounded. So this is what it means for compact support. So you can think of it as basically like, if I have a cloth, like look at this cloth, right? Yeah. So I'm gonna actually just make my own picture a bit bigger for this. Yeah. Okay. So if I have a surface that looks like this, I'm going to bend my camera down. Yeah. Okay. So right now it has 0 support, right? If I take my jar over here and I put it under, is it visible? Can you see the... Maybe if I just incline this a bit. Yeah, you see it, right? So, beyond the edges of this, right? This edge and this edge. So these both edges act as boundaries and the middle part acts as a support. So this is why the name is given a compact support. So the fact that it's bounded calls it compact. And the fact that it's raising it calls it support. Okay, so that's how you can think of compact support. Cool. So going back to the board. our deformations need to be strictly only things that have a length, things that preserve the length. That is like, this is an elastic surface in the sense that it allows for deformations. And if I stretch this, I cannot increase the length of my handkerchief. So these are the restrictions for deformations on 1D lines. So restrictions, okay, this is the rules for having elastic deformation on 1D lines. I put 1D over here. Okay. Now, as I've mentioned, if we go with this rule of deformation and we allow these kind of deformations, then what Euler has done, he's classified solutions, Euler's solutions, to minimal bending energy, You've seen in Ulrich's talk, the picture that I put in the last video. Let's go up and see where it is. Yeah, so you see this, right? So one is a straight line, one is this kind of line. So you can see that they all have compact support. The support that they have at each given interval, let's see if I can draw this. So over here, this has zero support. So zero support. This has compact support because this is the boundedness, right? Similarly, this is the boundedness for this. Similarly, this is the boundedness for this. And this is a little more harder to draw, so I'm not going to bother. This is closed, and this is basically closed. And the rest of these, all of these are compact. In the sense that we defined closed and closed curves, right, in the last class. So if I add it, so gamma of bar is equal to x plus b minus a, that whole business, something like that. Let's forget it. Similarly, with the same reason that I can't draw this, I'm not going to draw this, and I'm not going to draw this and not this. Oh, okay, so I can tell you the bounded part. So this is the compact support here, this is the compact support here, this is the compact support here. And this example is actually a really better example to understand compact support. So everywhere beyond here, it is equal to 0. And it is only in this region that it is greater than 0. And so it is finite because it's less than infinity. It doesn't like, if this is the curve, it doesn't straight blow up to infinity all the way before coming back down like that. So none of that business, right? So in this case, it would be greater, it would be tends to infinity. But in this case, it's less than infinity. So it's finite, it is non-zero. Okay. I hope this gave some sort of intuition, even if I was over-explaining quite a bit. Cool, so we talked about Euler's solution to minimal bending energy. And now I'm going to talk about Ulrich's generalization, or like basically what he introduces next. So what he introduces next is called framed curves. Now what are framed curves? We were talking in 1D the whole time, right? So in the case of framed curves, we try to make this higher dimensional. So this is 1D. And in framed curves, say I have a triangle-ish pipe over here. You can think of it as a pipe now, instead of having a wire. So something like this, I guess. Okay. So we're going to do a little shading here to show that this is hollow inside. And so this looks like a pipe. And you can think of it as a pipe, okay? A pipe with two different faces. An end face and a start face, I guess. Okay, so now the interesting about pipes is that I can start to twist my curve, right? This is now a new kind of deformation. If I have, do I have any wire? I probably do, I just can't find any. Yeah. So this looks like a pipe, right? And the reason I can twist it is that if I have a face like this, right? Oh, I'm gonna have to zoom in again. Yeah, cool. So I have a frame like this, then the act of me turning this part of the face, okay? So this is the pipe part, and let's assume this part has a face. This is one face and this is another face. So this is our first face, this is our end face. So now by twisting my end face, I start to introduce torsion. So torsion is the word for twisting energy. So what I'm going to do is that by slowly rotating one of these faces, I introduce torsion into my curve, and I hope the cable doesn't stop working as a result. But this is what torsion is, okay? So when I mean the torsion of a curve, I mean if I'm given a curve that looks like this, can I tell how much the angle of me rotating this face is? So to measure torsion, we take the angle at this side. Okay, let's take this as our fixed point, and we measure how much we rotate our cable. So that angle by which we rotate our cable, that is going to be our measure of a torsion. Okay. So let's get back to the board. And let's make some more space. Let's go down all the way. Cool. So when we start, trying to find the bending energy of a framed curve. Now you have to worry about both the face, then the actual pipe. It's better to think of them in terms of pipes. Okay, the pipe and then another face. So let's put a square like this. A triangle. And there's that. This, okay. Okay, cool. So if I just shade this part just for the sake of aesthetics. Okay, so this is our framed curve, okay? And now what I'm going to do is, instead of considering the whole curve, right, to measure the twisting that occurs. Oh, let's quickly check that is twisting a valid elastic deformation. Right. So as far as I can tell, the length is preserved, so that's a tick. Let's just write length preserving, or let's write isometric. That's the word, right? So isometric tick. And what is the other condition? It has to be isometric and it has to have compact support, right? So this seems very compact to me. The fact about compact is always you have to ask, is there a boundary? Is there a boundary, or does it continue at infinity? Right. So this clearly does not continue until infinity, right? This is a bounded line in the first place. So, and our compact support doesn't, it is bounded between the edges of this face. So that's a valid compact, that is a valid, elastic deformation. Hence twisting is yes, elastic deformation. Now, given that I'm twisting it, yes, how do I measure how much twist is there? So instead of looking at every point along here and trying to measure it, I'm going to measure something called internal torsion. So torsion is just the word for twisting, right? So internal torsion is the way of saying internal twisting. And what I mean by internal torsion is, I mean to say ki ignore everything that happens between here and this whole, over the length of the whole pipe, and I say consider only the faces. And I only want to measure how much these faces have rotated. So I'm going to take this face, right, from here. Then I'm going to take this face, that looks like this. And I'm going to measure the angle between them. So if this is facing upwards, This is facing like this after rotation. And so I put this, I measure its angle, and theta is your torsion. Okay, cool. So the interesting thing is, okay, so let me just chuck in some formalities, okay? So technically, instead of calling them faces, right? Now you're ready for to hear what it's actually called. These are called orthonormal moving frames. So the reason why we call them framed curves is because of these frames. So these faces, this triangle over here, is a frame. And then we say moving frames because, you know, you can take your cable and you can twist it around, do whatever you like. So I'm going to take the mouse now. I can twist it as in how I like. So that's what the moving word is for. Oh, my bad. Yeah. And yeah, that's what moving is for. And orthonormal is the fact that we make them parallel to each other. Okay. And then we measure its angle like this, and we call that torsion, or torsion, which is denoted by tau. Okay. Now there are different kinds of torsion, but this is the kind of torsion that we're interested in for this curve. So there are different ways of defining torsion depending on which context you're in. So that's what Ulrich mentioned. He sort of clarified while he was explaining we were using internal torsion and not Freinet torsion. So I don't know the difference between them, so I can't teach you anything about either of them. However, after that, Ulrich goes on to now say the bending energy of an elastic frame. So yeah, that was what I was writing before, right? Bending energy of a framed curve. So now B, or if you want B of gamma, or if you want E of gamma, is given by E of gamma. So what do you say? The frame curve is denoted by both the curve and the face. So the face is n. So I have to put in a little comma and n over here. Okay, cool. So this is given by the integral 0 over L double dash squared. So I hope this is all okay. This makes sense. Yeah, I hope so, because I wonder if I've provided enough motivation to explain why it looks like that. And now this is our normal. Okay, let's just take away the okay. This is our bending energy for gamma. Bending energy for gamma. That is without torsion. And now we add an extra part, and that looks like lambda, the whole integral 0 to L. And now we take the torsion squared. Okay. And we define tau as a total torsion when it is a difference in angle. So I had a triangle like this, right? This is the example I was taking. So giving you this angle like this. So total torsion is given by theta in this case, okay? So total torsion is defined as, let me write the definition, total torsion is equal to either the phase change or you could say the angle transport. From the start to the end. From the start to the end. Okay. Or angle of twist. Okay. So now we have understood our frame curves pretty well, right? And what we want to know is, okay, this is all well and good. How can we do the same? Let me write that. How can we do the same for surfaces? And our answer lies in finding the analog. So answer is find the analog or the counterpart of bending energy for 2D surface denoted sigma. So initially, what was our old thing? We had 1D curve gamma, and now we have a 2D surface sigma. So this is the old thing that we do not care about further, and we want to build on this to understand this, right? So similarly, now we need to ask the question, what do you say? What do we allow for deformation? So in what kind of bending is allowed for a surface, right? So the constraints are the following. Okay, constraints. Now the first constraint is, it is the same as before. We want it to be isometric. For instead of bending, let's use the word deformation. Okay, constraints for deformation, it needs to be isometric, right? It has to, instead of, so isometric as a word, iso means same, and metric means measure. So it means that it has the same measure. So if I say two curves are isometric to each other, it means they have the same length. If I say two polygons have this are isometric to each other, I say they have the same area, and so on. Cube and spheres, I will say volume, and so on. Okay, so this is all isometry. Okay, and so yeah, let me just scratch this away because this is not the important part. It's just a commentary. Okay, so that's what isometric means. Second, as you've guessed it, we need compact support. And now you're probably going to wonder, is this enough for, like, is this enough conditions on our kind of deformation? And the answer is no, because it turns out the next constraint you need to put is you need to put something called conformal deformations. So what conformal means, it means that it, what is that? It preserves angles. So an example is, okay, let me take an example of a square. Okay, yes, all angles are right angles here. So a conformal deformation of this is basically like if I'm stretching it like this. So this is conformal. However, for a non-conformal example, conformal, all I have to do is I have to somehow change it when I deform it. I have to change its angles now to deform it. So to give an example of non-conformal thing, all I have to do is I have to take this square and I have to maybe bend it a little like this, or like just skew it. Skew. So this is not conformal because now its angles have changed. Okay, simple. So this is what conformal deformations mean. I will probably show a picture now, or I'll attach a picture at the bottom just to show the difference between conformal and non-conformal. And the last one is that we have a surface, right? Say it looks like this, okay? Let's just say it has a hole over here. Let's not exactly a torus, okay? I don't know, I'm a little bad at providing examples of this. But what we want is that if we deform it like this, right? This deformation on, like, say something that looks planar. Okay, I say all this simply to just emphasize that, okay, this bulge you see here is a deformation. Right. And let's suppose it's conformal, compact, and isometric. Now, what I'm worried about is that if I start to mess with what happens in the boundary over here, right, then I can easily come up with non-elastic, non-elastic deformations. For example, when we were talking about deforming a line that looks like this, we always kept the endpoints fixed, right? So an analog of that is that we're keeping the boundary of our curve, delta of gamma, is fixed. Okay. Similarly, if this is my surface sigma, then I want delta of sigma to be fixed. Okay. So I want everything around here to be unchanged as a result of my deformation. Okay. So if this changes my deformation, then this is not elastic. So you can see this deformation is messing with our boundary, right? That is why it's not elastic. Okay. So the last thing, let me just scroll down and write it a little more neatly. Yeah, so just to be clear, the last condition is the boundary of surface sigma must be fixed. Okay, so that is our last condition. And so if we have a deformation that satisfies all of these, that deformation is now an elastic deformation. Elastic deformation. Okay, cool. And so an example of this is, say I have a surface that looks like this. You know, it's flat and stuff. Then an elastic deformation is going to look like this. So as you can see, this seems to be angle preserving. So if I have this as just, I'm just putting these contour lines so that I can keep track of making sure that they all intersect at the right angle. Yeah, so the angles are preserved, as you can see over here, this and this. So it's conformal. Right. Now around the boundary, around this boundary, everything is okay. They're both fixed. So boundary fixed, or I'll just write d sigma fixed. What else is there? We wanted the area to be the same, right? Yeah. And what else? We said boundary, we said end compact, yeah. So this, what do you say? This little bulge over here, it is bounded within this region, right? So it is compact support. So I had shown the example of taking a tissue, taking my handkerchief and putting a jar under it, right? So that is exactly what this image looks like, right? It looks like I'm putting a jar under this sheet with 2 holes. So, yeah. Okay, cool. So we're almost done with 1 page of Ulrich's notes. Yeah, just 1 page. Now, I'm going to introduce you to the fact that surfaces can have more than one kind of energy. Can have more than one kind of energy. Okay. And so now I'm going to introduce 2 things. Given a surface, say, I don't know how to draw a good enough surface to illustrate this example. Let me see if this is a good enough example, okay? So let me just take this smooth surface with 2 bulges over here, right? So, earlier we talked about radius of curvature, right, k. And if I look at the radius of curvature at everywhere else, say at this region, right? Then the radius of curvature in this region k, let this region be u, is equal to 0 because it is flat. Let's just assume this whole thing is flat except for these 2 bulges. Now as I approach this bulge, let's take this as u1, this will be u0. So radius of curvature at u1 is greater than radius of curvature at u0, which is equal to 0, right? And similarly, the higher I go up, the larger my radius of curvature becomes. So u2, ku2 is larger than ku1, right? It is also larger than ku2. u0, sorry. Okay, so yes. So the radius of curvature tells you in some sense how bulgy your region is, or not how bulgy your region is. In more specific cases, we would take a point x and we would say, we would draw a circle over here and we would take this radius such that this circle is tangent to sigma at the point x that belongs to sigma. Okay, so that's the idea. Alright, now if I measure, so what do you say? This is embedded in R3, right? This is a 3D surface. This is a 3D sort of illustration. Yeah. I have a 2D surface over here. However, it is embedded in 3D space because otherwise I have no way to actually talk about these bulgings. Right, they're rising up. They're 3D. So, yes. I have basically 2 ways to measure these things, measure these radiuses. So if I go along in this plane, or if I go along and if I measure the radius of curvature going this way, and if I measure the radius of curvature going like this way, or like just along this plane in general. So this is going to be my first principal curvature, and this is going to be my second principal curvature. And the reason why I can't explain it well is because I don't understand principal curvatures that well myself. So all I know is that if you have a surface and you're going to measure them in 2 of these intersecting planes, then all I understand is that K1 is like one of these is going to give you your principal curvature, and the other one is also going to give you your principal curvature. That is what I understand. And so, given a surface, you can calculate its curvature at all points in 2 ways. Given these principal curvatures, your Gaussian curvature is defined as the product of these 2 principal curvatures, and your mean curvature is defined as the average or the mean of your 2 curvatures. So this is denoted by h, and this is denoted by k. Okay. And I think maybe in the next episode, next lecture, I'll probably look at these things a little more deeper because I don't understand them. And only if I feel like I've understood them well enough, I'll probably continue on with that. Yeah, so I will just go ahead and finish the rest of this first page of Ulrich's notes, Ulrich's lecture. Yeah, so what I understand, now I'm going to go in blue. So the different energies of surface sigma is given in terms of h and k, which is your mean and your Gaussian curvatures. And so, for example, for a surface sigma, E of sigma is going to integrate, it's going to take 1/4, the whole integral over sigma, the first principle, so k1, first principle curvature, so kappa 1 squared plus kappa 2 squared. And this is the same as 1/4, the integral of h squared minus k by 2 squared. This is easy. All you have to do is you have to expand. We know k squared is equal to kappa 1 plus kappa 2 the whole square. The whole divided by 2 the whole square minus k by 2, which is just k1, k2 divided by 2. Right? So this is easy. I hope so. And this is equal to k1 squared plus k2 squared. Okay, cool. So this is this, and this is that, and this is equal to that. Okay. Now, yes, what is left? Yeah. So this is our bending energy. And a fact about this, which is what I understood from Ulrich's talk, is that this bending energy tells you how planar your sigma is. Okay. Now, I'm going to go more down. Okay, so E of sigma is going to tell you how planar this is, right? Similarly, you can define two more energies, okay? And the better term, so rather than calling it an energy, the term that's used is a functional. So this would be the energy functional. Energy functional given as E of sigma. Okay. Now similarly, we're going to define two new things. That is the Wilmore the Wilmore energies or Wilmore functionals. Okay. So the first one is omega, not omega, just W. W of F is given as the integral over this surface sigma of just the square of the mean curvature. Similarly, W with tilde of F is going to give you the integral over the surface of h square minus k. Okay, and so this energy measures how spherical, I think, how minimal your sigma is, and this measures how spherical your sigma is. Okay, And this concludes the page 1 of Ulrich's lecture. Okay, so let's just make some key points, things that I want to explore in the next lecture before I move on to the next page. Okay, so things to study better. Let's just scroll all the way up. Yeah, there we go. So, okay. Yeah, right, okay, cool. I got this. Okay, so the bending energy I feel is personally clear. I can probably cover that again if that doesn't make sense. The compact support also feels clear. I don't really want to explore that anymore. Homotopic, yes, okay, that I understand. Framed curves, I understand. Yes, so I want to understand internal torsion. I want to understand the difference between other kinds of torsion. I want to understand what lambda is over here because I'm not sure if he mentions it or not. Then total torsion I understand. How can we do the same for surfaces? Yeah, that makes sense to me. Conformal deformations, yeah. Only thing is I'm not really sure if I've explained this well. So you can tell if you don't understand. I want to understand how to calculate principal curvatures and mean curvatures. I just want to understand curvatures a lot better than I do right now. Because I don't think my definitions are right enough to distinguish between anything. Like I can't tell the difference between Gaussian curvature and mean curvature besides spitting the formula at you. So I'm going to have to learn that. And let me write that down. So we want to understand principal curvatures. We want to understand mean curvature. And we want to understand Gaussian curvature. Okay, what else is there? I think that's it. So yeah, thank you for watching and I will continue next time.